will introduce him.
Thank you, Michael. Hello, everyone. My name is Marta and I'm your ODH host today. I'm very happy to welcome you all, and especially our speaker, Massimo Chiaradia. So Massimo joined us from the University of Geneva in Switzerland, where he's a senior lecturer at the Department of Earth Sciences. He's also the 2020 SEG Thayer Lindsay Lecturer. So Massimo obtained his master's degree at the University of Padova in Italy and a PhD from the University of Freiburg in Switzerland. His research focuses on the pathogenesis of arc magmas with implications for continental crust formation and the relationship between magma chemistry, dynamics of subduction zones, and the formation of porphyry type deposits. To carry out his research, Massimo combines fieldwork with various analytical techniques, including petrography and or microscopy, mineral and rock chemistry, light and heavy stable isotopes, radiogenic isotopes, high precision radiometric dating, and petrological statistical modeling. Massimo has been accumulating a leading big picture understanding of how porphyry copper deposits form and what controls their metal endowments, which is what we'll share with us today. So without further ado, please, Massimo, the floor is yours.
Yeah, thank you very much, Marta. Thanks a lot to the organizer, and good morning or good afternoon, good evening to everybody around the world. I saw that there are many participants from different parts of the world, so thank you very much for being there. So what I will talk today is the results of my research during the last few years, in which I have become interested in one aspect of the formation of porphyry deposits. We know that scientifically and also from the exploration point of view, it's very important to know where and when these deposits form. But another question that has been little addressed is why these deposits have such a big range of endowments. These are just some extremes shown here to the left in terms of copper contents, and to the right in terms of gold contents. We have several orders of magnitude of difference. So what are the reasons that we find deposits with such large endowments? Of course, this is a huge question to answer. And what we have started to do is just a very simple modeling, petrological mass balance model, which is just a framework into which to work. Of course, the picture is so complex, there are so many parameters that our aim was just to provide a first order of ideas of what could be the main controls in causing such huge differences. So the rationale of our model is based on mass balance. And the starting point is the amount of metal that we observe in a certain deposit. And basically starting from that, we go backwards and we relate this final result, which is the ore deposit, to all different processes that are up valley of these, and they are related somehow to this final expression of the ore deposit. So we know that from several years of geochemical, of isotopic geological studies, that in porphyry deposit, these metals are essentially precipitated by magmatic derived fluids. So we can make a link between the amount of metals which are deposited and the fluids through the amount of fluid volume, the copper and gold concentration in these fluids, and the precipitation efficiency. So the link between these two parameters is mediated by these other parameters. And because, as I have said, that this fluid is of magmatic origin, of course, this must have some relationship with magma. And what mediates this relationship is the water solubility in the magma. Of course, the amount of magma, because this will control how much volume also or mass of fluid we have in the magma, the metal concentrations in the magma itself, and the partition coefficient, which determines how much of these metals will go from the magma into the fluid. And even going backwards, up valley, let's say, in this reasoning, we can also have and put some constraints on the amount of magmas that are produced in the crust using thermodynamic modeling. There are several models which have been developed, especially for arc magmas, that we can use and into which we can put the frame of this rationale. And overall, all this process, this is a very important part, is controlled also by timescales. So these processes must happen within reasonable timescales, which are geologically observed. And I would say that there are two important timescales. One is the timescales of the crustal evolution of the magma, so the timescales of melt productivity. And the other one is the timescale of generation of these deposits. Of course, even though this is a relatively simple model, there are so many parameters that are more or less loosely or more or less strictly constrained. And if we want to have a conservative approach and a reasonable approach, the best thing to do is to do stochastic modeling. So to allow many of these parameters to vary within a reasonable geologically constrained range. So we need this stochastic approach. And in the next slides, I will just go through one of some of these parameters that are listed here in this sketch, those which are probably the most important in controlling the overall model. So one first important thing is, of course, the metal content of the magmas. And this is shown here as an example for copper. So these points here, the blue points, are the results of the statistical treatment of several thousands of data, of bulk rock data from arc magmas, especially of thickness above 25 kilometers in the crust. And what we observe, because porphyry deposits form most of the time in these thick settings, even though we will see there are porphyry deposits that also form in thin arc settings. So basically the message here is that if we take these magmas, we can see that with the evolution, so differentiation of the magma, copper constantly decreases. And there has been a lot of studies showing this during the last years. So if we take into account typical intermediate to felsic magmas, which are those most of the time associated with porphyry deposits, we can see that the copper contents of these magmas are normal, and actually they are even lower than their parental magmas. Let's say something between 20 and 50 ppm. So is it still possible to form giant porphyry deposits using these normal magmas, or so we address the question starting from this point. Of course, any enrichment in the magma would be more than welcome, but what we observe basically is this. So we wanted to see whether what the overall message of arc magmas tell us can be used still to form giant porphyry deposits. Melt productivity constraints, as I have said, there are several models. What we used here is the model of Annen et al. In Journal of Petrology, 2006. Basically, this model starts from an average magmatic arc flux, which is shown here, the value, and the injection of magmas at different crustal depth. So what happens when we inject basalt continuously through time into the crust at different depth? Because of the existence of the thermal gradient, and we can take any average typical thermal gradient like 20 or 25 degrees per kilometers, for instance, we can see that when we inject magmas at different depth, they will start to cool. But the cooling will be differential depending on which part of the crust we are. Of course, if we are at shallow levels, because of the temperature contrast between the basalt, which has in the model a temperature of 1280 degrees, it will cool much more rapidly than if it is injected at a depth, let's say, of 30 kilometers, where we have a surrounding temperature of the rocks of around 600 degrees. So this results in a different evolution of the magmas. The basaltic melt injected will start to cool, will start to differentiate, but it will cool much more rapidly at shallow level than at deeper level. And because of the continuous injection of melt, eventually this will also eat up the surrounding rocks, and this eating up of the surrounding rocks will be much more efficient at the deep level than at shallow level. Overall, through time, this will result in residual melt which are accumulated at deep level from the fractional crystallization of basalts, which increase much more rapidly than those at shallower level. Additionally, the heating of the crust will lead eventually also to partial melting of the crust itself, and therefore the overall result will be a hybrid melt, a mixture of residual fractionating magma from the basalt and partial melt of the crust. So the results of the model are shown here in terms of melt productivity, which is the percentage of the melt which is produced with respect to the melt which is injected, and the duration of the injection at different levels. So the different levels are shown by the different color codes, which corresponds to different intervals of pressure. And of course, at any pressure, at any depth, we can see that the melt productivity increases through time because of this, of what I explained just now. And if we take the same time of the same duration of injection, we can see that, of course, the melt productivity is much more important at deeper levels, at higher pressure, than at shallower level, because of the existence of the thermal, geothermal gradient. There are also some geochemical constraints that we have tried to put into the model. One of the most used one is the strontium yttrium values. This is a collection of strontium yttrium values of rocks associated with the mineralization, the red diamond and the purple triangles, whereas all the other points are, let's say, not related to mineralization. And this is the work of Bob Laux, and we can see that overall, if we take the average of these populations, we can see that the porphyry copper rich deposits associated with the red diamonds have overall higher values than non-mineralized magmatic rocks. And this range here is the average 100 plus minus 1 standard deviation, which is more or less 50. Whereas gold-rich porphyries, quite interestingly, they are still more or less higher than not mineralized rocks, but they are significantly lower than the values of the magmatic rocks associated with copper-rich deposits. So more or less 50 plus minus 25. I will come back later to this point when I will try to compare the two kinds of deposits. For the moment, I stick to the copper-rich part. So how do we form these these high strontium yttrium values in these magmatic rocks associated with the porphyry deposit? So there has been a lot of debate on the origin of these rocks, but I think there is quite a consensus now about the fact that these high strontium yttrium values are essentially the results of differentiation of magmas at different depth. And because essentially there are minerals which are more or less stable at different pressure. In particular, we can take as an example plagioclase here and amphibole, because these are two of the main players in causing these variable strontium yttrium values, because strontium is highly compatible into plagioclase, whereas yttrium is highly compatible in garnet and also in tritanites and in more or less in amphibole. So the differential stability of these minerals will cause, during differentiation through fractional crystallization, but also partial melting, different kind of strontium yttrium values. So if we take an evolution at shallow depth, where plagioclase is stable at relatively, or it's quite close to the liquidus, is much earlier than amphibole, we will have strontium yttrium values that will decrease with the differentiation of the magmas. At the intermediate pressure, we will have a slight increase, because more or less the two minerals here and other minerals come close to the liquidus together. And eventually at high pressure, we will have a strong increase in strontium yttrium because of the fact that mineral phases like garnet, amphibole start to crystallize very close to the liquids and therefore deplete the residual melt in yttrium, whereas plagioclase doesn't crystallize and therefore the strontium will strongly increase in the residual melt. So we input these parameters, so these curves shown here are derived from a combination of experimental petrology in which different mineral phases were observed by crystallizing them of cooling the melt at different pressure and using different a range of KDs available from the literature from these two elements. If we combine the two now, another important aspect to consider is maybe the time scales of precursor magmatism. We can see here some data shown for more or less large porphyry type deposits like El Teniente and Yanacocha, and the values of strontium yttrium in the magmatic rocks compared to the ages of these of the magmatism. So what we observe often in these deposits is that there is a quite long precursor magmatic activity, and the mineralization usually comes towards the end of these magmatic cycles. And another interesting thing is that the strontium yttrium steadily increases through time. And interestingly, the slope of strontium yttrium versus the duration of the magmatic activity is similar for those deposits for which we have these data available. We have carried out recently some work on a complex, on a magmatic complex, volcanic complex in Ecuador called Chachimbiro, because these show very resemblant evolution to typical large porphyry systems, with an increase in silica and increase in strontium yttrium through time. The only difference is that this happens through a much shorter time scale, 1 order of magnitude less than this mineralized system, so causing a slope which is much more steeper. And apparently there is no mineralization associated with this. So it could be that really the duration of this magmatic activity and a slow ramp up of these parameters are telling us something about the evolution of the magmas at depth, which is more favorable or less favorable to form porphyry deposits. And, we will see that in the results of the modeling soon. Another very important input in the model, of course, is the water solubility. We have used the model of Newman and Lowenstern here, which shows the dependence of water solubility in silicate melt from pressure, and also the dependence on different melt composition, showing that more felsic magma can contain at the same pressure higher dissolved amounts of water compared to the more mafic ones. So all these parameters were input with a stochastic approach into the model, and these are the results of the model in one plot. So the plot shown here is on the y-axis the pressure of magma accumulation or the depth of magma injection, which is shown here, and on the x-axis is the duration of the magma injection at different depths. And the points here are hundreds of thousands of simulations carried out with this approach, and the color codes indicate magmatic magmas which are associated with the fluids containing potentially or able to exalt potentially these different amounts of copper. So low copper in blue and increasingly higher amounts up to 240 million tons of copper in the pink part of the simulation. So what of this shows us that the magmatic systems which are the most fertile in this model are the pink ones, of course, and are those which are formed at higher depth, more than 0.4 about gigapascal, and requiring also a longer time of injection. So why is it so? The answer is quite simple. If we look at what we have seen before, This corresponds nothing else than more or less to increasing amounts of volumes of magma which are accumulated in the deep crust. And of course, we can accumulate much more magma at deep crustal level than at shallow crustal level. And these are the equilines of volumes of these magmas accumulated. And even more clear is the correlation between the exsolvable copper and the amount of water that is associated with these magmatic systems. So the deeper we go and the longer we accumulate these magmas at depth, the more water we can accumulate also in these reservoirs. Interestingly, what came out from the model is also this concerning the geochemical part of the modeling is that the most fertile magmas are those which fall within the range 50 to 150, which is exactly what the natural porphyry deposit data suggest. So I will come back later to explain then what does this mean. Another way to look at the results of this modeling is shown here, in which we have now on the x-axis the excess water, and on the y-axis the pressure or depth of emplacement of these magmatic systems. We can see that there is an important dividing lines at about 0.4 gigapascal. So the green part here indicate excess waters, which are negative, which means that the system is water undersaturated. The red part is water saturated. And we can see that above 0.4 gigapascal, all the simulations virtually produce water saturated systems. So these magmas, when they are accumulated at this relatively shallow level, virtually they exhaust continuously water. Whereas the most fertile ones are those, the pink ones, that are accumulated below or at higher depth than corresponding to 0.4 gigapascal, and they are always water undersaturated. So these magmas essentially are water undersaturated. These are water saturated continuously in the model. How does this translate in terms of copper? This is shown here. So to the left, we have these magmatic systems that develop at less than 0.4 gigapascal. And these are the simulations here in this plot of overall duration of ore deposition versus exsolvable copper in the fluid, or the copper measured in the deposits. So what we see that assuming different precipitation efficiencies for the simulations, 50% the colors coded part and 100% the black line, we can see that we can never reach the rate of copper precipitation in actual deposits. So this basically means that magmatic systems which are accumulated at shallow depth, they can exalt copper, but they cannot exalt copper enough rapidly to explain the formation, especially of the largest deposit. Maybe we could explain the formation of these deposits, but not of the largest one, and the overall trend of porphyry deposits in this plot. In contrast, if we take the magmatic systems which are developed at deeper level, these have potentially enough water to exsolve copper during the duration measured for porphyry deposit formation, to exsolve copper enough with a rate which is sufficient to explain the trend of porphyry copper deposits for efficiencies between 50 and maybe 60, 70%. So in this plot, we can also see isolines of different color, black, yellow, and white, which indicates the duration of magma accumulation at depth. So we can see that in theory, to form the largest deposits, those of the Andes, we need accumulation times that are above 4 million years, or on the order of at least 4 million years. Whereas the other ones could be formed with accumulation times which are shorter. What happens if we plot a real accumulation time, which can be measured through precursor magmatic activity in a kind of plot of time of accumulations versus exsolvable copper? So what we can see that is that for the deposit for which we have data, most of them indicate this long magmatic activity of several million of years. However, we can see also a very interesting thing is that the fact that we have long accumulation time doesn't necessarily result in always in very high copper endowment. We can see that for the same duration, we can have relatively small deposits and supergiant behemotian deposits. So the message here is that we can have a lot of magma here, but what is important is that this magma is water undersaturated. And of course, it doesn't produce a porphyry deposit if it stays down there. It must come up to shallower level to form the so-called parental magma chamber from which we have these offshoots of the porphyry fingers that are those which are forming the mineralization itself. If this magma stays down, it will never form a deposit. So probably this is telling us how much of this magma which is accumulated down is brought up efficiently to shallower level to form a deposit, or it remains locked at deeper levels. And more recently, we have carried out some investigations, some modeling to understand what is the importance of or what is the rate of injection of the magma from the deep reservoir to the shallower one to produce these deposits. So, and the results are quite interesting in the sense that they are shown in this plot here now, which is the same as we have seen before. So the overall duration of ore deposition versus the copper endowment, and the points are the different deposits. And now the color codes correspond to different magma injection rates, which are calculated based on the amount of magma that needs to precipitate in our model these amounts of copper. And we can see that all the deposits fall in this purple region, which corresponds to high injection magmatic rate from the deep to the shallower crust, which usually could correspond to large eruptions. Of course, a large eruption would not allow the formation of these deposits. So this suggests somehow that even though we have a very high magmatic injection rates that are required from our model, these may not result in catastrophic eruptions. And these results go in the same direction as results shown in recent works, like those from Simon Large for Bingham, which based on thermal modeling of zircon have shown that they require similar high magmatic injection rate into the shallower crust to form this deposit. So how to solve this apparent contradiction? Well, one possible answer comes from modeling, which has been carried out also quite recently, which shows that if we have a long period of thermal preconditioning of the crust through magmatic activity in the lower crust, we will mature also the upper crust, and we will precondition it to prepare it to receive high fluxes of magmas without necessarily erupting it. So at the end, probably we have that the long-term accumulation of magma at deep levels is very important, because on one hand, it will accumulate these huge amounts of magma, which are necessary to accumulate the copper and the fluids necessary to form the deposits. And at the same time, this will determine the precondition of the upper crust that will allow subsequently the transfer of this huge amount of magmas within the time scales measured for the porphyry deposits, which correspond to relatively high magma injection rates, which usually could result in large eruptions, but they do not, because of this long-lived magmatic activity, which probably preconditioned thermally the upper crust. So basically, we have a two-step model: accumulation in the deep crust, which is probably favored during period of long compression, and this is a long-term known thing in porphyry deposits, that they are associated with the precursor long compression periods, and the subsequent transfer to shallower level during a transition from compression to more neutral stress regime. And maybe at a large geodynamic scales, this could be caused by several parameters. These are some ideas proposed by Rosenbaum and Cook the role of the subduction of aseismic ridges in producing compression and changes in the stress and their association with porphyry deposit. But probably there are other parameters which could play a role. However, the main point here is the two-step formation of this in this model, which probably requires some tectonic trigger at the end to transfer this magma from depth to shallower level, which could have some answer in this kind of processes here to the right. Okay, so what about now coming back to sumetrium? We can see here then why these magmas with the specific interval of sumetrium values are so fertile. Actually, in our simulation, they correspond to magmas which have the highest amount of volume, the highest volume produced in our modeling, and also those which have the highest amount of exsolvable water. So sumetrium is nothing else probably than a proxy for the buildup of large amounts of magma, which are very water rich in the deep crust, and therefore they are very fertile. Does our model also reasonably match with the real data? We think that it does quite well. This is shown here in these two plots. This is again a copper endowment versus sumetrium of magma, and we can see our modeling here and the real data, which follow quite closely the same shape. We can also, by slicing this plot for different intervals of sumetrium values, 0 to 50, 50 to 150, and more than 150, we can also make probability plots using the density of our simulations and also the probability distribution coming from the real deposits. And we can see that there is a quite good match for all the three slices with the largest deposits that can be formed only within this 50 to 150 interval for the reasons explained above. This is shown also here now in a plot of duration of the ore mineralization versus sumetrium, which shows quite a good coincidence between the color codes of our simulations, which indicate different endowments, and the color codes of the real deposits, which fall within those endowments. So we can see a good correspondence, even though there are sometimes some exceptions which could indicate some other processes which are at play for these deposits. So I come now to the second part of my talk, which is the difference between the copper-rich versus gold-rich porphyry copper-gold deposit. So I became interested in the fact that we have some porphyry deposits which are more enriched in gold and others which are more enriched in copper, and this is shown here in this broad map. And there are regions of the Earth which have very different copper-gold or gold-copper ratios, like the Andes here. If we take all these deposits, we have an average of gold-copper ratio in terms of million tons about of 10, and here about of 80. And so I have started to plot data available from the literature and found actually that porphyry copper-gold deposits seem to form two distinct trends. One, which is in a copper versus gold endowment plot. One, which is enriched in copper and quite poor in gold, and the other one, which is rich in gold and relatively poor in copper. Another interesting thing which came out is that this trend is essentially only associated with calc-alkaline magmas, whereas this trend is associated with both calc-alkaline and alkaline magmas, or variably alkaline magmas. And interestingly, the 6 largest deposits of this gold-rich trend are all associated with variably alkaline magmas. We can see this dichotomy also in this other plot for data which are available. Now we have ore duration versus ore versus gold tonnages. Again, we can see two distinct trends with a much higher rate of gold deposition in the gold-rich trend than in the copper-rich trend. And a further difference that we observe is also in the associated magmatic rocks that we have anticipated also before. And if you remember, we have seen that the gold-rich porphyry deposits are characterized by magmatic rocks with overall lower strontium values compared to the copper rich. So I will try to explain all these in the frame of a comparative model between the two kind of porphyry deposits. So among different possibilities, one reasonably possibility is that the two trends are caused by different precipitation efficiencies of gold versus copper in the two kind of deposits. So the green dots here are the results of simulations starting from calc-alkaline magmas with depth of evolution down up to 30 kilometers depth. And we can see that we can reproduce the two trends for the copper, the gold poor and the gold rich porphyry deposits associated with calc-alkaline magmas by considering a 12-time better efficiency of gold precipitation in these deposits than in these. However, what we can see is that starting from calc-alkaline magmas, we cannot explain the formation of much higher gold endowments in this trend. To reach these high gold endowments, we need to start from magmas which are more gold rich since the beginning. In this case, this is justified by the fact that alkaline magmas indeed are characterized overall by average higher gold contents. So this might suggest that there is not only a question of better precipitation efficiency, but also some kind of petrogenetic control in the formation of these gold-rich porphyry deposits associated with the alkaline magmas especially. So why is it so? One possible answer has come from a work of about 10 years ago, Murakami. They already showed that there is some kind of correlation between the copper-gold ratio in porphyry deposits and the depth of emplacement of the deposits. So shallower deposits are gold richer, as shown here, than deeper deposits. And they explain this in terms of a kind of decoupling of copper and gold during fluid exolution, either at deep or at shallow level. So little decoupling at shallow level, which would co-precipitate copper and gold, and the decoupling at deeper level where copper would precipitate, whereas gold would remain in solution and eventually ascend to shallower level. However, another important thing that we see here now, in this plot, I have slightly changed. I added another information. I added the information about the endowments, which is shown by the size of the circles. So large circles are larger endowments, of course, in terms of gold. So what we can see is that, yes, we have gold richer deposits at shallower level, but we have also a broad range of gold endowments within this shallow level environment. And the result of this is again probably linked to the temporal duration of the magmatic hydrothermal event. So we have some data which tell us that this is the case for copper, with the increasing endowments which are associated with longer time scales of formation of these deposits. And these new data show also that there is probably something similar also for gold. And this goes in the direction of several studies suggesting that these deposits are incrementally constructed through different steps of intrusion, repeated intrusion, and magmatic hydrothermal events, which have short duration, each one, but cumulatively they build up these deposits incrementally. And the largest is the duration of this repeated cycle. Probably the largest is the deposit. Coming back to the strontium question, there is another interesting aspect which comes out. Well, there are several studies which have shown that there is some sort of correlation between the strontium values of magmatic rocks and arc thickness, which could indicate, which has been used as a proxy for crustal thickness, but to myself probably indicates more the depth of evolution of the magmas within a variably thick crust. Of course, if we have very low strontium values, it means either that the crust it is thin, or that if it is thick, the magmas, even under this thick crust, has evolved at shallower level because of more extensional conditions. But the interesting thing is that if we plot now the depth of emplacement of porphyries, which is derived from fluid inclusion studies, from geological information, versus the strong sumetrium of the associated magmatic rocks, so two completely independent parameters, we observe that there is a correlation, which indicates that the porphyry deposits, the gold-rich porphyry deposits emplaced at shallower levels, are also associated with the lower strontium metrium values, which suggest the evolution of the magmatic system at shallower level. Whereas the copper richest deposit, the copper largest deposits, are not only formed at deeper level, but also are associated with magmas that are formed or have evolved at the overall deeper crustal level. So this could have an implication also, another possible explanation for the differentiation between gold-rich and copper-rich deposits, which is shown schematically and simplistically here. And this relates to the relative timing of sulphide saturation versus fluid exhaustion. So this is shown here in these two plots to the left. We have the sulfur content in the residual melt and the sulfur content at sulphide saturation, which is simplistically modeled to illustrate this process. So when the two cross cut, this means that we reach a sulphide saturation, and therefore to the left of this we have a residual melt. To the left of this we have precipitation of sulphide. And in the bottom part we have, in contrast, the water saturation. And we have different curves which correspond to magmatic evolution at different depths. So you can see that these are high depth and these are increasingly shallower depth. At high depth, so fluid saturation, water saturation is never reached, or only at very, very high differentiation degrees. Whereas at increasingly shallower depth, we reach fluid saturation at increasingly early stage of magma evolution. So why this is important? Because this translates in quite a different behavior of copper and gold. So this is now the copper and gold behavior during differentiation of the magma, taking into account the sulphide saturation. So we can see that the impact of sulphide saturation is relatively minor for copper, because copper has not such a high affinity for magmatic sulphides, but is dramatic for gold, because gold has a 2 orders of magnitude higher affinity than copper for magmatic sulphides. Therefore, if we have a fluid saturation that comes after the sulphide saturation, like is the case for the deep magmas, deep evolving magmas, this will be completely depleted in gold, and they cannot form any gold deposit probably if they can come up to shallower level. In contrast, they will still have enough copper to exsolve it. And there is, of course, here a trade-off between the amount of copper and the amount of water that is accumulated within this magma. So this seems to be still possible for copper, but not for gold. So if, in contrast, if we start to exsolve fluids much earlier, because the magmatic system evolves at shallower depth before the sulphide saturation, then we can efficiently strip the gold from the magmatic system. And this is summarized in this paper that we published recently, in which we have this broad two different environment, a thick crust, which is the most favorable for the formation of the largest copper-rich deposits, especially when it is associated with long-lived compression, which accumulates magma at deep levels, and then eventually the transfer to shallower levels to form these huge copper systems. Thin crust and or extension in thicker crust maybe leads to overall smaller magmatic systems, which result in smaller amounts of copper, but in very high endowment of gold. And overall, the lifetime of the two systems is also different. These are much longer lived here at shallower level, up to 2 million years, whereas these seem to be much shorter lived, up to 500,000 years. And this is essentially the result of the different thermal state of these magmatic systems, which occur in a much thicker crust than in this magmatic system. But in both cases, the formation of these deposits seem to be a cumulative, incrementally built up of several pulses of magmatic hydrothermal fluids. So I leave you with this final slide, and I thank you very much for your attention.
Thank you very much, Massimo, for this great talk. As we move into the discussion section, you can see how to ask your questions in the chat. Be free to ask questions. And I would like now to directly invite an expert on modeling of porphyry deposits to get the discussion started. So I'll ask Dr. Philip Weiss to unmute himself. So Philip is a senior researcher at GEFSET and is an expert on numerical modeling, well known by for the development of numerical simulations in porphyry systems. So Philip, if you want to get the question started, go ahead.
Well, thanks a lot. And thanks a lot, Massimo, for this very impressive talk. As always, it's great to see well, what you're doing, what you've done. And it's so impressive that it always reminds me that I have to reread some of your papers to really understand, because it's so complex. So yeah, I was asked to spontaneously to ask some questions. So one thing I always wonder is, I think it's a beautiful story that you have to sort of prepare stuff, the magma and the melts in the lower crust before you bring it up to the upper crust. And so one question I always have is magma flux crucial there? I mean, it's important to have lots of magma so that it can evolve. And then there's always the question of duration and how much volume you create. But is there a sweet spot, the magma fluxes you need? Or can you, if you have lower mass magma fluxes, if you just have more time, because its volume is then duration times magma flux. Are there sweet spots for what happens in the lower crust and then the transfer to the upper crust?
Hi, Philip, first of all.
Yeah.
Nice to see you again. Yeah, thanks for the question. Yeah, indeed, what we used is the average long-term magma flux that is coming from several studies. Of course, we know that sometimes there are higher magma fluxes, and we have also tried to model this. I didn't have time to talk about this, but in the sketch that I show here, yeah, basically I talked about this part. But we also modeled this situation in which you might have sometimes very high transient fluxes. So again, this is a work of Annen and a group a few years ago. But other studies have also shown that these magma fluxes are high, can only be transient, because otherwise they will result in eruption. So they will not result in buildup of magma at depth, which stays at depth. So, but we have modeled for short durations up to 200,000 years. And actually, again, under these conditions, we see that even increasing the magma fluxes, you have a quite fast exhaustion of fluids, which can explain relatively, we are talking about giant deposits, but not the behemotian one like El Teniente or Chuquicamata. You can go up to 10 million tons copper, but you cannot ever explain the largest one, just because there is not enough time, even in under these conditions, to accumulate enough fluid and metals. So what we approached is, we think that the most likely scenario is this one, in which we take this, which is an average. It doesn't mean that it's always the same, but it's an average, a long-term average flux in which there might be fluctuations, but which result in a more stable system that allows the buildup of large accumulations at deep levels.
But if you would take this flux and divide it by 2, but then multiply the duration by 2, would that in that model of the evolution result in the same fertile magma? I understand that if the fluxes are too high, you get eruptions, but if you take a longer time and a smaller flux, that would still work geochemically and in the
yeah, absolutely. In theory, yes. From the mass balance point of view, absolutely, it would work.
Yeah, but in terms of energy balance, maybe in cooling rates, is that where you get the sweet spot?
Yeah, exactly. Yeah, maybe it doesn't sustain enough so it would cool more rapidly, and therefore it would have a trade-off with the buildup of residual melt, or even the melting of the crust, because of the energetic constraint if you have a lower input of magma. So now what is quite interesting is that we come up with time scales of a precursor magmatic activity which are quite consistent with what we observe in these long-lived giant deposits. We have a track record from magmatic activity that is always on the order of 4 or 5 million years, which is somewhat consistent with the magma flux, which is taken here, which results in this kind of buildup of magma.
Yeah. Maybe another question, with the idea that you develop a fertile magma in the low crust, then you bring it to the upper crust. Would you actually expect that then we would see some copper-rich or gold-rich material in fluid inclusions and melt inclusions? Because I remember, well, most systems we have studied are ore deposits, but there are a few studies on barren systems. And there, one of the conclusions was that, well, the fluids and the melts are not particularly different than the ones. How would you like to comment on that? Would you expect, or is there no contradiction there?
Yeah, it's a good point. It's why there are so many batholithic rocks that they contain water because they have amphibole biotite, but they have no mineralization on top. So yeah, this is a really for me it remains something which needs to be explained. It's not completely clear to me how there should be some kind of small mineralization, even under these conditions. It's not that the water stays there. I don't know really to tell you the truth. It remains enigmatic.
Well, that's maybe where the hydrothermal system comes into play, because ultimately we need to focus these fluids. I mean, that's what I'm looking at mostly.
Absolutely.
And I personally think that there's a connection between magma fluxes and how that feeds the feedbacks, the interplay with the magmatic hydrothermal system. Then that all of that has to be in line to make a really giant deposit.
Yeah.
Okay. So I'll leave it. There's probably other people that also want to ask some questions. So thanks a lot, Massimo. It's great to see you.
Thank you. Great to see you.
Thank you very much, Philip, for agreeing to do this spontaneously. See you in a few minutes. So we'll go ahead now with the questions from the chat. We have many here, so let's go by order. So Azam, do you want to unmute yourself and ask your question?
Yes, thank you very much, Massimo, for this informative talk. So I'm just wondering, what would be the role of the deep crustal faulting systems in this scenario. I'm based in Ecuador, so doing a very big regional project here. So that you're very right, because you see the bathyletic rocks that they do have biotite in them, and by default, no mineralization is reported. But if you just pay a little bit more detailed attention, you're going to see tiny little things around, specifically recently through the artisanal minings around here. So it's a little bit weird to compare the big ones that are in association with mineralization systems and the smaller ones that almost following the same pattern. So we see a range of intrusive rocks, from having biotite in them, not having biotite in them. So it's a little bit confusing. But the interesting thing, regionally speaking, is that when we get a gigantic deposit, for example, the new discovery of Alpala deposit in Cascabel district is very associated with faulting systems. And I'm just wondering how you're gonna interpret this in this context.
Absolutely, yeah. I think that geodynamic tectonics and creating faulting and stress specific in the crust are essential ingredients of all this. We couldn't or we didn't address this point. Of course, we are not structural geologists, but we know that all these systems actually are strongly controlled by tectonic features. And I think that the role of focusing of magmas into the same place, into the crust and the fluids, is essential, played by this structure. So what we try to provide is a very general scheme, but of course in this scheme, additional parameters like structures, faults, they play an essential role to enhance and to focus all these parameters into the same place. We need a lot of energy, a lot of fluid, a lot of magma, a lot of metal to put into the same place to form a deposit. Otherwise, it will be dispersed into a too much large area to form a deposit. So you are completely right that this is essential.
Yep, thank you.
Thanks. You. So we have a few other questions. One, Raju PVS, do you want to unmute yourself? No. So he asks, do we expect copper deposits to contain gold at depth? Massimo, you can answer.
Well, as I've shown from these general plots, we have quite a specific trends from available data, at least. Okay, so these copper-rich deposit, they contain gold, but they never contain so much gold as the shallower ones, apparently. Apparently, because there is maybe this double role. One is the depth of evolution of the magmas, which reaches sulfide saturation before fluid saturation, and therefore the gold is stripped off. And the other is further enhanced probably by this decoupling between copper and gold at the phase exhaustion stage, as shown by the Murakami study. So it seems from the data available that it is likely that when you have this high copper system, very high copper system, you usually get a little gold, and vice versa.
Okay. Very good. Another question from Craig McEwen. Would you like to unmute yourself? No. So he asks, your models do not contemplate any influences of host rocks to the magma chambers, generating the porphyry, copper, and gold deposits. Do you think the process of forming porphyry copper could be influenced by host rock chemistry, redox state, etc.?
yeah, I think, yeah, there are several studies which have shown in some deposits specifically the influence of host rocks, especially as I remember, some gold-rich deposits, which are the reduced type gold deposits, which are affected by the host rock chemistry. So I think that absolutely in some cases, again, you have local controls which might result in aberrations or exceptions to this general model. We didn't take into account this impact, but I am completely aware that local redox reactions can change these figures. But still, I am convinced that the main part is the result of this first order scale, upon which we can build up differences based on local geology, absolutely.
Mm. So another question by Caesar Witt. Would you like to unmute yourself?
Yeah, okay. Hi,
Hola, Cesar.
Hola, ¿cómo
Nice to
estás?
see you.
Very interesting and instructive presentation. I have learned a lot of things today. I have just a small question. How do you think that the juvenile versus recycled magmas get into the equation? And so, and the other is, how do you think that studying zircon geochemistry, mostly by isotopes like hafnium and oxygen, can help into defining this the probability of getting gold or copper-rich deposits?
Yeah, thanks. Well, you know, there is a huge amount of literature coming out in these last years about zircon geochemistry as a tracer for porphyry identification, for fertility of magmatic. They are based on essentially on rare earth, mostly ratio between rare earth, which indicate water-rich systems and oxidized systems. So absolutely, there is a lot of work going on there. Concerning isotopes, I think, well, it's more difficult there because I think it's mostly a question of maturation of the magma. And of course, this depends a lot. So, I mean, what our model shows is that you need a lot of maturation of magma to build up a lot of magma. So this will, of course, result also in interaction with the crust. But the interaction of the crust will depend on the place of the earth where you are. And you know, in Ecuador, for instance, the crust is very thick, but is also very primitive. So isotopes are difficult to use there because they are very similar. The isotopic composition of the incoming magmas are quite similar to the isotopic composition of the crust. Whereas in the central Andes, maybe you have a crust which is more contrasted isotopically, and this might result in different isotopic responses. But still, the processes are probably the same. So it's more difficult, I think, to apply isotopic studies because they indicate a process which in some cases might be masked by the composition of the crust.
Okay, thank you, Massimo.
Thank you. There's another question from John McIntyre. Would you like to unmute yourself?
I've just unmuted myself.
Sorry, go ahead.
Yeah, the question relates to the second question from the first questioner, where he asked, what if we had half the magma flux for twice the time? And of course, one of the problems is that gets you out of the sweet spot. But what if that lower rate of magma flux was coming from a series of magma pulses, so that each pulse might have a short-term flux similar to a system in the sweet spot, but then there was a gap before the next pulse came?
Yeah, I think that then the response of the system wouldn't be the same as this one, because you would have enough time to cool it down, and you would have to start again all the job which was done by the previous pulse. So I think it's quite important that the way that you inject the magma into either in a steady state or as a series of short-lived pulses. It's quite important. But
Right.
what we use is actually what we observe, actually, that this is the average rate of into which, as I said, there could be some role for like a spot or very short-lived high sustained fluxes. But I think that we need to have more studies in that, combining geochronology of the formation of the ore deposits with the timing of potential happening of these processes in the mantle, like a higher subduction rates, and this is quite difficult. Or subduction of serpentinite, water-rich serpentinite, which could result in higher fluxes of water into the mantle and therefore higher melt production. But combining the two, I think, is quite difficult, because you can date the deposits, but these deep processes are very difficult to date and to compare with the timing of deposit formation.
Right, many thanks. A great talk, by the way. I was just fascinated.
Thank you.
Thank you, John, for your question. Massimo, we are going over the time. Is okay for you to continue, because we have still many questions in the chat?
Yeah, for 10 minutes, then I have to leave you. I have to get my daughter from school.
Okay, so we'll ask probably 2 more questions. We have a question from John Menzies in the chat. John, do you want to unmute yourself and ask?
Yeah, fantastic talk, Massimo.
Hi, John. Thanks.
Yeah, I guess the question goes to some degree to the efficiency of the metal deposition process in the epithermal environment. I guess the question is, if you have calc alkaline magmas with reasonably prospective strontium, yttrium, and vanadium scandium ratios, and have developed very large high sulfidation alteration systems, is it reasonable to expect that there would be entirely barren endomembers with virtually no metal deposition whatsoever? Or would you expect to find at least some copper someplace within the system, given the overall efficiency of it?
You mean if you have magmatic systems with the typical fertile geochemical signatures, if they always result in a mineralization or not, basically?
Yes,
yes.
Not necessarily economic, but at least some within the system.
I think, yeah, but this was the main reason we wanted to investigate this Ecuadorian complex. That was very interesting from the point of view of geochemical prospectivity, of geochemical fertility, because it had all the characteristics of porphyry deposits, high strontium ramping up. The only difference was exactly this much shorter time scale. So I think in theory, yes, absolutely, because these are very water-rich systems, so they could produce some sort of alteration and mineralization. The only thing that, well, we didn't observe, but maybe is deeper in that is not exposed. The only thing that I think is that the time scales of all these processes is very important to build up the size of the system. So I can expect that there is something, but I think that the relationship between the time scale and the size is important.
And where was the deposits, the particular intrusions you were talking about? Sorry, I missed that.
Oh, is in Ecuador. Is in northern Ecuador, north of Quito. Is a is a quaternary complex, is 400,000 years old, down to 4,000 years. So it has a lifespan of about 400,000 years.
And fully evolved, fully developed alteration systems.
There are not really. We couldn't see strong alteration systems there, but maybe they're maybe deeper. I don't know, but we couldn't see exposed to the surface. These are volcanic rocks, essentially. We didn't see any no intrusion is exposed, not even a porphyry. Yeah, these are only eruptive products.
Okay, thank you very much.
Thank you.
Thank you, John, for your question. I think we have to wrap up. There is no more time. There is a question from Ben Williamson that maybe can send a question by email. We'd like to thank Massimo for this great talk and agreeing in being here today. And
thanks to you.
Thank you. And everyone, there is the link for the certificates in the chat if you need that. And have a nice day. Thank you all for being here.